All right. Good morning, ladies and gentlemen, to everybody out there in virtual land. Beautiful day out there, but stay in your house. Welcome back to your favorite class. Okay, generally, a couple of announcements. One, all my hair fell off. No, this is like the prison Mike Kevin look, for those of you that watch The Office. Yeah, so all my hair fell off, but I'm much more aerodynamic now. So as an aerospace engineer, that makes me happy. Announcement number two, your midterm was on Friday. Generally a pretty good job. It was a little bit long, so I gave you some points back there. And I'm kind of trying to push on you guys a little bit. I mean, I want to know who knows it really well and separate the people that know it extremely well from those that know it very well, from those that know it in okay. All right, so I needed to kind of push a little bit on the exam to see sort of where we were, and generally, good job. Scores were a little low, so I bumped it up. I'm not trying to bust anyone's nuts here. You guys are all putting in a lot of good work. I'm happy with what you're doing. So no one's in danger of failing the class, not even close. No one's within 20 points of failing the class. So don't worry about the exam scores. Generally, you guys did very well. I was very impressed. And what I'll say is that this exam, the one you just took, is going to be much more difficult than the one that'll come up at the end of the course, because the last exam that we went through was kind of like the end of the ringer. All right, so we went through all the math, we went through all that nonsense about integrals and summations and matrix math and a lot of complicated laminate theory, man. Complicated. God, my head hurts. All right, we went through all that complicated stuff, and you made it through. All right, you're out on the other side now. And so I was kind of debating a little bit this week about what material I wanted to do. I was back and forth between working on sandwich structures and working on maybe some less mathy stuff. Sandwich structures is kind of like an extension of laminate theory, and it's actually a little bit more complicated form of laminate theory because you have to sort of now incorporate shear stresses, which are kind of across the face of the thick sandwich structure. And, we'll talk to that when we get it. So instead of like bombarding you with additional like crazy math, I thought maybe we just chill a little bit and talk about something else. All right. So, composites are complicated in their math, obviously, but there are other complicating things about composites that also make them interesting. And some of those things include like the way that composites are fabricated. Now, we talked a lot about manufacturing methods in 429, and we sort of glossed over a lot of the materials that go into composites, but we didn't really go in a lot of depth on like what those materials are and why we decide like, hey, this epoxy here has the ratio of 100 to 25 by mass, and we have to blast it at 150 C for 3 hours for it to be cured. Okay, we just sort of like took that as gospel and said, okay, the data sheet says so, so I must do it this way. All right. This week, we're going to talk about cure kinetics and rheological models. And cure kinetics and rheological models are sort of the basis for how composites are manufactured and fabricated. Okay, so cure kinetics being like the rate of reaction of an epoxy inside of like the composite. So it's going to determine things like how long do I need to manufacture this thing? What temperature do I need to manufacture this thing? What is the mix ratio of part A of my epoxy to part B of my epoxy? Like all these sort of things that go into the manufacturing process that are important. And you can actually quantify a lot of information about why do I need this much of this much of this, why do I have to spend this temperature, this time to cure this particular mixture, and all those sorts of things. And so that's what we're actually going to sort of step back and talk about this week. So a little bit less intense like matrix math and algebra and all that sort of stuff. And we got to kind of like go back to the roots of like your chemistry class, and maybe at the end of this week you'll be begging me for that math back. I don't know. After we like start talking about chemistry and some of the cure kinetics models, maybe you'll be like, all right, go back to that other stuff. Like the matrix was way better. All right, I like that. I can do that in MATLAB. All right, so we'll see. I don't know, a little bit different flavor this week. So we'll see how it goes. I did post the notes for the cure kinetics, so you can find those on Blackboard now. They're like 20 slides long, something like that. And hopefully we get through all of those this week. And later today, I'll post a homework on cure kinetics, which is the stuff we're going to talk about this week, which will be due next Monday. The solutions for the exam were posted, so if you want to take a look, go ahead. I would normally maybe talk about it right now, but I want to move on. I'm over it, okay? I'm over it. Are you over it? Okay. You want to cry a little bit? Okay, me too. But mostly because I can't go outside. Okay, let's continue. Any questions in the chat? Got an email from me for with your information about kind of the things you missed on the first test. Okay, so if there's no discussion, let us breach this new topic. Okay, and the new topic today is pure kinetics and rheological models. Don't worry if you don't know what this word is. Rheological. You will soon. All right, pure kinetics and rheological models. So like I said, most composites can have a variety of different chemistries that are made from, right? So we talk a lot about epoxy chemistries and epoxy amine chemistries. There are other chemistries. There's, vinyl esters, there's imidazole reactants, there's all sorts of crazy stuff out there, okay? But overwhelmingly, if you're going to work on a structural material, it's going to be epoxy, fiber reinforced epoxy, okay? So I will say that there are many different types of chemistries that make up composites, but we're going to focus our discussion on epoxy and amines. All right. And so here I'll say the focus on epoxy. Oh gosh, spelling is hard. Plus amine chemistry. All right. There are other types, like I said. So besides epoxies, there's vinyl esters. You could even think about like thermoplastics. That's kind of entirely different. There are other part B reactants. Okay, so if you want to think of like the epoxy as part A and the amine as part B, there are other part B reactants, which might be things like hydroxyl groups. You might have imidazole, etc. Okay, we laid out a bunch of these in the 429 class, different part A's, different part B's. And the point is that like all of these guys, there's tons and tons of different combinations of like all of these things, so on and so forth. But most of the high-end aerospace composites will have this type of chemistry, this epoxy and amine chemistry. So that's what we're going to focus on in this class, kind of sticking with the continuous fiber reinforced epoxy and amine composites. All right, so that's the focus here. Now let's kind of give a definition on pure kinetics so we're all kind of on the same page. So what we're going to sort of discuss first is pure kinetics. And this is pretty simple and hopefully something you've seen before in your chemistry class, at least on a very basic level. And this is the rate of a chemical reaction. Whenever we're talking about kinetics, we're talking about the rate of a reaction. And specifically for composites, we put this pure kinetics in front of it. So for us, this is the rate of reaction of a polymerization or a curing reaction. So rate of reaction for curing, and I'll put here in parentheses polymerization chemistries. All right, and these pure kinetics can depend on so many things, so many, right? Obviously, like the reactants that make up the reaction will drive the cure chemistry. Okay, so that's obvious. So it depends on the following: the reactants, obviously. It can depend on the temperature at which the reaction proceeds, right? We know that molecules generally are more active at higher temperatures, and so kinetics usually increase. The rate of reaction usually increases with temperature. It can depend on other initiators or accelerators or catalysts. Okay, so catalyst, accelerator, And for some polymers, you can actually incorporate inhibitors to slow reaction down. It's kind of like the opposite of a catalyst. And of the three of these, actually, like this inhibitor is really the most important. We'll talk a little bit about this later, but we know that a reaction between, let's say, an epoxy and amine, if you ever done this at home, if you ever had like a 5-minute epoxy or whatever, and you just kind of like put the two parts together, you like mix it in a little tin or whatever, and it comes together, it's hot, okay? And that's because this reaction is generally exothermic, and at higher temperatures the reaction will proceed more quickly. And so sometimes you need to like slow the reaction down, you need to like chill it out, okay? Because if it goes too quickly, it'll heat up, causing it to go even faster, and then it'll just be cured in like a matter of seconds. All right. So the inhibitors sometimes are included to really just like, hey man, we got to just chill. We got to slow our roll here. We're proceeding a little too fast. If you don't just chill out, we're going to get too hot. It's going to run away, and it's going to be bad business. All right. So inhibitors also important. All right. One other thing that influences kinetics, and this is sort of a minor interaction, is pressure. And I'll say that this is minor, a minor interaction. So pressure is related to temperature, and really it's the temperature that drives things, but there are some chemical species that are pressure sensitive, and it can have some minor interactions. All right. So all these things sort of influence the rate of reaction of particular species. We're mostly going to focus on this. All right. We don't really have time to even dive in on these sorts of things, inhibitors, accelerators, and catalysts. That's a whole field of study in chemistry. I mean, polymerization chemistry, polymer physics. This is like people get PhDs working on this sort of stuff. Okay, so that's a whole nother level. What we want to focus on are what's going on with the reactants, meaning what is the proper ratio of these two particular things based on what we know about the individual reactants, and how does the reaction proceed given a certain temperature, and can we come up with a model for that that is somewhat simplistic. All right, so that's where we're going to kind of focus our energy. All right, so why are Cure kinetics important? Well, I kind of mentioned this, but I'll reinforce it, is that the Cure kinetics tell you things like how much of part A do I need to mix with part B? And if I mix them together, how long is it going to be before they're fully solid? Okay. And what happens if I add temperature? Does it, increase the rate? How fast? And that's important for things like how long is it going to take me to manufacture this composite? Okay. So if I think that it's going to take me 4 hours to manufacture a composite, but it actually only takes 45 minutes, well, I'm wasting 3 hours and 15 minutes every single time I go through the manufacturing process by holding this thing at time and temperature much longer than I need. So it's very important from like an economic standpoint for businesses to really fully understand like what is the reaction chemistry, why does it take this long amount of time for it to work. Okay, so it's important for um, estimating resin viscosity, because the kinetics models will also help you estimate what the viscosity of the resin is, and this is useful for manufacturing. If your viscosity is too high, you may not get the resin to flow where you want it to go. All right, so processes like Vardum, for instance, for those of you that remember Vardum from 429, can be difficult if you don't understand what the viscosity is going to be. All right, so obviously the working time is important for the resin you're working with, the total manufacturing time. And it's also important, and we'll talk about this later, for secondary bonding operations. Let's consider a composite that we cure to 90%. If it's 90% cured, that means that 10% of the chemicals inside of that epoxy are still left over for the potential to react. Okay, so if we're 90% cured and I take a composite that's 90% cured and I slap it against another composite that's 90% cured, they're going to have the ability to chemically bond at that interface because they have like 10% reactants left over to interact at that surface. So this is called secondary bonding or co-bonding or co-curing. Kind of goes by a lot of different names. And if you want to leverage these sorts of operations, you need to know, well, how long do I need to cure this composite so that I get it to 90%? And how much do I need to cure this guy so it gets to 90%? So now when I slap them together and hold them together for a certain amount of time, now we can get it to 100% fully cured where there's actually additional bonding between the two different layers. All right, so I'll say here that it's important for leveraging advanced bonding techniques. I feel like a therapist. You guys want to learn some new bonding techniques? All right. So that's kind of the motivation for what we're doing. Now let's dive in and focus our attention on epoxy. And we're going to, again, like I said, go back to the roots and really break it down to the chemicals and very basic level on why the ratios are what they are, what dictates what the ratios would be, and then from there we can talk about the timing required for doing each of these possible reactions. Okay, so we're going to focus our attention on epoxy chemistry. All right, and epoxy is one of the two reactants that go into fabricating your epoxy solid. Okay, so the word epoxy really floats around a lot. And that when you create a hardened structure, which is like part A plus part B creating this solid plastic, you call this like an epoxy. All right, so you've made this hardened piece, you tap on it, it sounds like plastic. Here, I got a piece here. Okay, so this is, can you hear that? Yeah, okay, so that's like hardened epoxy. All right, but in actuality, epoxy is like the liquid part A component of a two-part mixture. So we're going to discuss it as the liquid part A of a two-part thermoset reaction. Okay, so when you're creating something solid, you want epoxy plus some other reactant here getting you the solid. All right, now this other thing over here can be many things, like I discussed before. We're going to focus on what will be the amine later. This is going to be our focus for our class, but for now, I just want to talk about sort of this part A component, which is the epoxy, all right, this liquid component. So an epoxy itself, the chemistry is based around what are called epoxide moieties. All right, so I'm going to bring in a picture here and show you guys what this looks like. All right, so an epoxy chemical contains, I don't know if I want to say millions, but let's just say many, epoxide moieties. Maybe you heard the word moiety in chemistry, maybe you didn't. That's not the right thing. Ta-da! I know we're all engineers, we don't like to look at this, but this here is an epoxide moiety. All right, a moiety is like a group of molecules that are kind of working together that have a general purpose, or they provide some information together as a unit. Okay, so this is a part of a molecule that is a bigger molecule. All right, so the epoxide itself is this triangular piece, right? This here is the epoxide. All right, it is this. Remember, when you don't see a molecule at a node, this is a carbon, and this is a carbon. All right, so we have two carbons and an oxygen coming together to kind of form this triangle of power. All right, Link would approve of this. All right, the triforce of CCO. All right. Now, the thing about these epoxide moieties, and I guess I should also make a mention here that these guys here, these R's, it's a pirate's favorite moiety. R. All right. These here are, they're just in chemistry called R groups. All right. And they are any other portion of the molecule that's related to this particular moiety. Okay. So with this moiety, we've got these two carbons here and here. They can handle two additional R groups just because of the covalent bonding and sharing between that carbon molecule and the other two sites available to it for covalent bonding. So it has two more additional sites for these R groups to work through. And these R groups are sort of what give the epoxy its actual character. And so I'll say these R groups uh, are there, and they vary substantially. Between epoxy types. Okay, so I might have a liquid epoxy here that's got some R groups that are coming off of it that make it uniquely different from this liquid epoxy over here that's got R groups in a different arrangement. Okay, so it drives all of the different character of the epoxy itself. So these drive the character of the epoxy. And these R groups can be all sorts of stuff. I mean, it's mostly organic compounds, so things like carbons, nitrogens, but there can even be some heavy metals in there, like ruthenium, and like some of the cobalt is common. There can be some other like crazy sort of elements that come into these, the backbones that create these liquid epoxies that we use. All right. And they really control the character of the epoxy. They change the molecular weight, they change the density, they change chemical resistance, all sort of stuff. So molecular weight, they'll change because of that the density. They'll affect the chemical resistance. Of the final product, so on and so forth. They'll affect mechanical properties. They really drive a lot of the character of the composites, these particular R groups. All right. And because these R groups can be so many different things, they can be crazy. These guys really control the product. And there are greater than, I don't know, 10,000 types of epoxies. And what I mean by epoxy is the liquid part A component that makes up the two-part reaction to get you a final solid plastic. All right. There are so many types of epoxies. I mean, so many. The most common, by far, that is used in most manufacturing process is called diglycidyl ether of bisphenol A. Exciting name. It's a mouthful. The most common epoxy for fabricating composites is diglycidyl ether of bisphenol A. And for short, it's usually just called DGBA. D-G-E-B-A. You guys ever get those water bottles, like those Nalgene bottles, and it has a sticker on it that says BPA free? You know what BPA stands for? Bisphenol A. Okay. So epoxy components can, in large doses, be toxic. All right. So if you have a lot of unreacted epoxy components inside of your product, meaning I have an excess amount of epoxy and I don't have enough part B reactant to fully react all of those things, then you're going to have excess amount of like bisphenol A floating around that is unreactive. And so like, let's say that I make a Nalgene bottle using this particular chemical and I have a bad mix ratio. Like for whatever reason, the amine didn't come through to fully polymerize this monomer. Okay. Well, if that's the case, I've got a lot of this excess bisphenol A kind of floating around that's in large doses toxic to humans. I pour my hot coffee into my Nalgene, which, probably shouldn't be doing anyways, and I drink that, and now I'm getting all this bisphenol A in my system, which in large doses can be very bad. So when you see all those BPA-free stickers and all that sort of stuff, now you can tell all your friends, hey, I know that that's, bisphenol A, and it's a component that's in epoxies and so on and so forth. Okay, that's the most common reactant, and this is what it looks like. All right, don't worry about drawing this guy. I'm just going to talk about it. So here it is. A couple of things that you'll see straight away on this guy. Here is your epoxide moiety. Same thing over here. All right. And so that means that all of this here is your R group. So if I wanted to represent this molecule chemically, I might just do that. Okay. Same thing, except the R is a stand-in for all this stuff, right? That's kind of the way that chemistry folks do it. And the way that they do it is because if I'm going to use this particular molecule in a reaction, well, the pieces that are important to me are this moiety and this moiety, because those two moieties are the pieces that are going to be involved in the chemical reaction. The other stuff, the R groups, they're just hanging out. They're chilling. All right. They're not participating in the reaction in any way because they're not chemically favored or chemically designed to participate in the reaction. They're just there to give additional character to the final product. Okay. So things here like phenyl rings. All right. Those guys are phenyl rings. Maybe you talked about those in chemistry, maybe you didn't. But phenyl rings are very chemically stable. It is very difficult to open those rings. All right. Those are 6-membered carbon rings that are very, very difficult to cleave and to open. That's what gives epoxy, typically, its very good chemical resistance, is that you have these very stable molecules in the backbone that are kind of hanging out and provide this incredible resistance to these chemicals that exist in the world. All right. There you go. There's a little introduction to epoxies and why they're so awesome. Now let's talk about how they actually react. We have these moieties, these epoxide moieties here and here, and they are going to be participating in a chemical reaction. And we can see just by the picture that, okay, here we have these phenyl rings, right? Phenyl rings are very stable. And that's because the configuration of the atoms is very chill. All right. They're comfortable with how much space they have and how far away they are from their nearest neighbor. Okay. They got enough social distancing from the other carbon atoms where they're like, all right, you're not close to me. You're not close to me. I don't need any space. I'm cool. I'm chilling. All right. That's different from these epoxide molecules. All right. Now you've got like these really close oxygen carbon triangle where it's like, dude, you're too close to me. Dude, you're too close to me. We need to do something. We need to like break apart. All right. Now that's the basis for how these epoxides react. Is you've got this triangle that's under like super high strain. Okay, it like really wants to just spring open and pop open, and it doesn't want to be by, it doesn't want to be in such close proximity. So the way that these epoxies actually react is that these triangles like spring open and move into action to sort of polymerize. All right. So let's talk about the actual reaction. Okay, this COC epoxide moiety if we talk in mechanics terms, it's under a high strain. All right, much like me, it is not stable. Okay. Okay, it wants to spring open. It's like bringing magnets close together. Okay, at some point, like the magnets, they don't want to touch each other. Okay, they want to repel and they want to break off. All right, that's exactly what these particular epoxide moieties want to do also. All right, we're going to talk about the reactants to spring open that epoxide molecule, and there are many. Okay, many reactants will do this. Okay, we will focus on amine chemistry. Okay, so there are many types of amines even themselves, and let's just draw what some of those might be. Amines are typically classified by the number of available sites they have for reacting. Okay, so typically you'll see primary amines, secondary amines, tertiary amines, and some other various types, but those are kind of the most common. All right, so most common are primary and secondary amines. And secondary. All right, so a primary amine group just looks like this. It's given by the chemical symbol RNH2. So RNH2, and this guy usually has some additional elements on it. All right, so that's a primary amine. And then the secondary amine is going to be RNH, where this has another R group. Let's call it R prime. All right, so this really only has like one site available to it, one hydrogen to pop off. This guy has two hydrogens to pop off. All right. So the hydrogens are what sort of participate in the reaction between the amine and the epoxy. So let's actually look at what this really looks like. All right. So I'm going to copy this down here. And actually, I want to see if I can crop this. So I only want to take in the amine reactions. Okay. I'm not going to try to draw this because my chemical drawing skills, not so good. All right. The idea here is that here we have primary amine epoxy addition and we have secondary amine epoxy addition. So like I said, this epoxide moiety is under a tremendous amount of strain. It wants to spring open. It wants to pop open. Okay. And the way that it pops open is with one of these hydrogens that's hanging out on the nitrogen. All right. So an NH2 group or an NH group is available to relieve that tension that's in the epoxide moiety by springing it open and transforming the oxygen into a hydroxide group. Okay, so one of the hydrogens comes from here and springs this guy open, and then this remaining guy who is going to spring open has to kind of go somewhere, and so he comes over and rebonds with the nitrogen. All right, so the way that that looks is one of these hydrogens is going to pop onto this portion of the oxygen, so we have this hydroxide group that kind of is created. Okay, so here one of them goes here, the other one remains on the nitrogen here. So now we've gone from an NH2 to an NH. So one of the hydrogens remains. And this portion of the molecule now has sprung open. It no longer exists. And this guy is going to go and bond with the nitrogen. All right. So here we see that bond that has occurred now after the triangle has sprung open. All right, that's the general way that this is working. And now we see that these two molecules are connected because that bond sprung open and went with the nitrogen. All right, that's kind of how that works. All right, the secondary amine reaction occurs in a similar way, except now we only have one hydrogen to work with. Okay, so here's your single hydrogen now that's going to come and attack this oxygen. Here it's going to then become this hydroxide group, and then this reaction now creates this bond between the nitrogen and what was the epoxide moiety. And now that amine is completely used up, there's no more hydrogens left for reaction, and we still have those R groups that are hanging out from the original structure, which is here. All right, that's kind of the way that this works chemically. All right, that's the focus of kind of what we're doing. And this is a small scale version of it. So how does it work on the larger scale? Okay, well, we can see here that we might have one primary amine that has two hydrogens available for work. All right, so if we have one molecule that can participate in to spring open two epoxide moieties, then we need less of component one than we do of component two. Okay, that sort of makes sense. This is why it's very common to see like a 2-to-1 mix ratio of like epoxy to amine, because you have like two hydrogens that are available over here from the amine to react with the one epoxide molecule, and you would need two epoxide molecules to sort of go with the one amine molecule. All right, so that's why it's very common to see much more epoxy required than the curing agent or the amine or the hardener agent. All right, that part two. So we see here for primary amines, there's two hydrogens available to react. All right, so it takes two epoxide moieties to handle this one primary amine. This is generally why you need less of the part B component than you need of the part A component. Less amine, and I'll say part B for more epoxy, which is part A. Okay, so if you ever buy like a chemical reaction system and you have a part A and a part B, usually it'll say on the data sheet, mix 100 parts of A with 30 parts of B. Okay, that's because there's a lot more chemical reactivity of that amine to handle the moieties that are in the epoxy groups. And typically because the epoxy groups have like all this extra crap along with them, they like way more per moiety available than the amines. Okay, so that's another reason. They have a higher molecular weight than the amines typically do, meaning that they're much less reactivity dense than the amine is. All right. So that's kind of a small scale on how they react. Let's look at what this chain looks like on a larger scale. So let's consider something like, oh, I don't know. I'm going to react this guy. Okay, remember this is DGEBA, my diglycidyl ether of bisphenol A. It's the common backbone of the most simplistic epoxy. If you just like Google Digiba and you want to purchase it directly, you can get like a gallon of it if you want. Don't drink it. Okay. So here's my Digiba, and let's say I'm going to react this with a primary amine. All right. And so our primary amines look something like this guy here. Okay, there's your primary amine. And so I'm going to sort of draw this generically with the amine that has two reactive groups on either end. Okay, so it can be sort of represented in this way, which is H2N bonded with my R group, which is whatever it is in the middle, bonded with NH2, giving me some final product. Okay, so here, this is like a primary amine here. And also, because this R group is long, we have another primary amine here. What you'll notice about the Digiba is that we have two epoxide moieties. We have one here and one here, right? So now how many of each of these do I need if I'm going to proceed with some reaction? All right. Well, if I have, let's say, capital N of these, then I have 2N epoxide moieties. All right. And I need, let's say I have M of these. In this particular amine situation, which is just kind of the most basic amine that you could possibly have, I have four reactive hydrogens. All right. So that means then I need 2 times as much epoxide, or 2 times as many Digiba molecules as this primary amine molecule. All right. So would need 2 times as many Digiba molecules as amine molecules. All right. So this gives you a general idea of what you would need. Now I'm going to draw this in a simplistic fashion, and we can see how the polymerization would actually occur given some available number of molecules to us. All right. So we'll say that we have 2N times our Digiba here, plus what would be like 1N of our amine, which here is H2N, whatever R group I have in the middle there, and H2. And notice these R groups are not the same. All right, so if we call this R1, let's call this R2. They're obviously not the same. And for on the left-hand side, we have the Digiba molecule. On the right-hand side, we could have whatever primary amine junk that we want in there as well. And let's say that we're going to react these. Okay. Well, the way this is going to work is the amine will sort of be the backbone upon which all of the epoxides gather. I'm going to do my best to draw this. It just might kind of take a second. And this R2 group, this guy here, will kind of become the backbone. All right. And so let's say to the north of him, he's got that nitrogen. To the south of him, he's got that nitrogen. And the two hydrogens that are attached to each one of those nitrogens will attack an epoxide moiety from each of the digiba molecules. Okay. So we'll get sort of a digiba that's coming on here, a digiba that's coming on here, a digiba that's coming on here, and one that's coming on here. All right. So we'll have these sort of 4 attachment points for the epoxide moieties. All right, so one is going to attach here, and remember when I create this, there's a hydroxide group that's formed, and then here's R1. All right, here's a hydroxide group, here's R1. Hydroxide group, R1. Hydroxide group, R1. And the idea here is that this continues over and over and over and over as we go through the polymerization. So it's going to have this reaction. And again, on the other side of this R1, there's again a similar looking reaction. So I've looked at one side of it, right? Now the other side can kind of go through the same thing, right? So these are kind of half of the original epoxide molecules that I had, all right? So it's 1/2 of the 4, right? So this is reacting with, okay, again, I'm going to get another OH, and I will here be connected to another nitrogen, which will be connected to an R2 group, which is connected to another nitrogen, which again makes another hydroxide group, which goes to another R1, so on and so forth. Over and over and over and over, okay? This is the general way in which we create a solid polymer, okay? These epoxide groups are reacting with the amine moieties and kind of springing themselves open to connect everything together, okay? So this would be like one of the original digiba molecules that has now reacted. All right, so there's one, here's 2, here's 1/2 of 1, 1/2 of 1, 1/2 of 1, 1/2 of 1. All right, so on and so forth. All right, so those were the original molecules, and the moieties were here, and they sprung open to connect with the amines. All right, so that's generally the way that the reaction will proceed. Right, a lot of chemistry today. Hopefully we sort of like brushed that off a little bit, but maybe you can sort of understand now a little bit with a little bit more depth of like, why do we need a 2-to-1 ratio or a 3-to-1 ratio of epoxy to amine? And it's because the epoxies have a lot less reactivity in sort of a density manner. So that's kind of the takeaway today. All right, chemistry, yay, good times. Next time when we come back, we'll talk about how we can actually model the rate of this chemical reaction that I've drawn. All right, so we'll talk about the exothermic nature of this reaction, how we can track how much heat is coming off of the reaction to tell us the amount of cure that we have given the certain amount of heat that has been released. Okay, so that's it for today. Thanks for coming by. Hope you enjoyed a little bit different style today. It was more chemistry instead of your hard matrix math. So like I said, it's going to get a little different from going forward. All right, thanks for coming.